Hello all, and thank you for being here. My name is Donika Mirdita, and I will introduce our work on RPKI validators on behalf of my team and I. One fundamental but little talked about aspect of the RPKI infrastructure is built-in limits and thresholds. RPKI is an infrastructure poised to handle large sensitive data that needs to be periodically and efficiently distributed among participants. But the logistics of supporting this stream of information in full deployment still needs to be figured out. Before we go to the core of our paper, I want to provide a quick overview of what RPKI is and how it works. So RPKI is a standard developed to protect the BGP from prefix hijacks. It relies on the issuance and distribution of cryptographically signed objects called ROAs, which are a mapping between autonomous systems and the prefixes that they own. The serving of ROAs is done via publication points, each of which is responsible for issuing and serving a subset of global ROAs. Publication points are organized in a hierarchical way and are queried according to their order in the RPKI tree of repositories. And finally, we have relaying parties or validators, the middleware which stands between the distributed RPKI content and routers. Relaying parties are tasked with periodically fetching the RPKI data, parsing, validating, and then sending the results to routers so they can protect their tables from bogus BGP announcements. However, RPKI can be attacked in different ways by exploiting built-in thresholds and timeouts in the relaying party software. Stalling attacks against RPKI are not new per se, and the community has tried to introduce measures, specifically through the introduction of default thresholds, such as RPKI tree depth and even timeout for individual connections. However, these thresholds were arbitrarily chosen. Not only do they not prevent attacks, but they also enable new ones. For example, tree depth might be limited, but breadth is still unconstrained. Relaying party individual connections have built-in timeout tolerances that can range from 5 minutes to hours depending on the relaying party being used. By limiting download bandwidth or simply stalling HTTP connections in tandem with a large malicious RPKI subtree, any attacker can slow down validation long enough to ensure objects such as manifests expire. Manifests notoriously have a very short validity period, with over 50% of them being valid for a day or less. So manifest expiration will ultimately force relaying parties to flush the content of the affected certificate authorities. We further observed another arbitrary threshold that could be exploited in a more creative way, one of which is what we call the delta snapshot attack. We observed that independent of the amount of ROAS in a publication point, the complete first-time full download of all objects is always considerably expensive, and a malicious entity is able to continuously trigger the worst-case download exploiting about 20% of all publication points. These are publication points that directly serve external clients. Major relaying parties, such as Routinator and RPKI client, have arbitrary delta thresholds of 100 and 300 delta files, respectively. Exploiting these relatively easily triggered delta to snapshot fallback thresholds leads to slowing down of the validation interval. One way to mitigate this problem of stalling due to malicious exploitation of thresholds is by introducing a more intelligent approach to validation intervals. Instead of naive tree traversal, the validation process could account for historical latencies for every publication point. This allows us to weigh them according to performance and penalize those that slow down the process by kicking them to the back of the execution queue. At the same time, the algorithm should also allow the repositories to redeem themselves, so to speak, after the network issues or the attack is over. They can redeem themselves the moment that their latency goes back to historical norms, and then they can get bumped up the execution queue. An important requirement is multi-threading and asynchronous processing of publication points. Our simulations show that the total time required to discriminate malicious publication points is roughly equivalent to the theoretical stalling time of all the adversarial publication points per thread. On this slide, I have included a figure showing the simulated process in given 4 malicious repositories. The top row shows that naive multithreading can help somewhat with speeding up validation despite adversarial publication points, but that does not guarantee legitimate publication points will be processed in a timely manner. The bottom row simulates the effect of our sorting limit algorithm with multithreading. By prioritizing publication points with lower processing times, the number of required threads to defeat an attack can be further reduced. Even with a single thread, an adversary can ultimately only prevent the update of its own repositories, as all other benign repositories have already been processed. Given the current issues we found with regards to thresholds, we decided to make some projections on full RPKI deployment. Right now, about 30% of networks enforce ROV and less than 40% of all IPv4 and IPv6 prefixes are covered by ROAS. Under a full deployment, we expect the number of ROAS to almost triple. And of course, the dataset will increase with additional tens of thousands of helper files and certificate authorities. But that's not all. The number of publication points should also increase drastically. Now, there are different scenarios that could play out with regards to publication point distribution, but one of them is the following. Due to the fact that publication points issue and serve a unique subset of global ROAS, the presence of large publication points that host RPKI content for the majority of the internet introduces single points of failure that can take down BGP protection for large swaths of the internet in case of targeted attacks or even network errors. Therefore, there is an inherent incentive to decentralize RPKI content hosting. At some point, best practices and even legislation could impose regulations on decentralizing critical infrastructure. Given that there are about 100,000 allocated autonomous systems, 60 to 70,000 of whom are actively being advertised, we estimate that if at least 10% of them would self-host their own repositories, we could get up to 10,000 publication points on the internet. The technology to do this, called delegated RPKI modus, already exists and is pretty stable and mature. Relaying parties need to periodically refresh their cache as well. At least once an hour is the status quo right now. So they would end up having to query thousands of publication points, and even assuming a best case scenario where each relaying party only needs 1 to 2 seconds per publication point, we still end up with hours-long validation intervals. Due to deliberate or accidental stalling because of aforementioned restrictive thresholds, and even packet losses due to heavy network usage, we can feasibly end up in situations when manifests expire and are not adequately re-downloaded, thereby downgrading RPKI protection. The number of relaying parties is also expected to increase dramatically. In general, autonomous systems do not rely on one single relaying party instance, but they instantiate several. In particular, the larger and more security-sensitive companies such as Amazon or Meta can use up to 50 or 100 relaying parties per autonomous system. Assuming then that from the 70,000 existing actively advertised autonomous systems, each of them runs at least 2 relaying parties, we land at a maximum of 140,000 relaying parties. And even more conservative approaches will still land you in the 6 digits. Full deployment of RPKI also introduces large local RPKI data caches. We estimate about 9 gigabytes, which would mean that in the grand total, over 1,200 terabytes of data transfer will have to take place over months to initialize all the 140,000 projected relaying parties. And then afterwards, even for periodic low-volume validation cycles, such as mere delta updates, we would have at least 700 megabytes of transmitted data from every publication point for every refresh interval. Our projections highlight that even a conservative future estimation of RPKI data introduces continuous large network loads that are unavoidable. RPKI data is highly dynamic, which means the relaying parties need to query all publication points multiple times a day to have an up-to-date cache. Attackers manipulating the arbitrary thresholds can further exacerbate this already large traffic. And while RPKI right now focuses on servicing ROAS, and in fact even our estimates are based on ROA projections, we expect to see the service expand further in the future to support additional BGP security protocols like BGP-SEC or ASPA. All of this is just more unaccounted for system load during full deployment. All in all, existing thresholds are too permissive in that they allow for a multitude of attacks that will only get easier and worse with increased deployment. But they are also strict enough that can cause download and connection errors for legitimate entities. It is important to find the right balance, and arbitrary thresholds are not the solution. In this work, we highlight the need for systemic work in formalizing operations thresholds for RPKI by introducing new threshold-fueled attacks. we also propose a redesign of the validation process that addresses, at least in part, existing security issues. Thank you for your attention.